Good afternoon. Welcome to course Thermodynamics of Materials. Today we are into lecture 157 and 158. We are discussing last day the problems based on phase diagram, and and we have finished that problem too. Last day we finished this problem, but only I wanted to additionally give the graphical representation of this problem, of this solution. Okay, this problem too. Remember this gold and silicon. Okay, I am not reading the problem anymore. Just what I want to tell you, see the answers. Okay, see these are the two questions, question A and question B. Question A is calculate the integral molar free energy of the eutectic melt. This melt, eutectic melt, and you know the composition is this is silicon is 0.186 here, and its gold is the balance 0.814. So of that eutectic melt, relative to 1 mole of unmixed liquid and liquid gold and liquid silicon. So this was the first question, and the second question was with respect to 1 mole of unmixed solid gold and solid silicon. These answers we obtain. This is for the A. The first one with respect to what I told you, when it is said relative to, with respect to means minus taking away. So this is the free energy of this relative to this, that is unmixed gold liquid and silicon liquid 1 mole. Okay, and this is 1 mole of the eutectic solution or eutectic liquid. So this difference answer is 11,300 joule per mole. This is completed. And with respect to the second part B, with respect to relative to 1 mole of unmixed solid gold and solid silicon, this is here B. So this is again, see, this is the same liquid means this liquid, eutectic solution gold relative to gold solid and silicon solid. Okay, in short, that is actually 1 mole together. So this is the unmixed solid. This is with respect to unmixed solid. This is with respect to unmixed liquid. What is the answer? Zero, because this is the explanation I gave. I should not repeat. Actually, instead I should focus on showing you the graphical representation. So it will be very satisfying then, because you actually drew free energy versus composition diagram. So here also the same thing I am doing here. See, follow. This is the diagram. See, I have written here graphical representation. This is today's class. Actually, I actually start today's class as a graphical representation, free energy versus composition diagram, uh, based on this problem. Okay, with respect to this problem, temperature is 636 K. That is, we always actually draw the diagram, this activity, free energy versus composition diagram for a given temperature. This temperature chosen is 636 K, that eutectic temperature. This we have considered. So let us follow the procedure that previous procedure. What is this? Our standard procedure that I told you. First, you assign zero values for in either side, gold side and silicon side, which will be assigned 0. Since these are this temperature 636 is below the melting points of either of them, gold here and silicon there. So gold solid is assigned a 0 value. So free energy of gold solid pure, obviously standard state 0, and likewise the other side also 0, this silicon. So both solids are 0. So if you connect this line, join this point and this point, then this is actually the unmixed gold solid and liquid solid, which will always fall on the 0 line. Okay, any combination of actually gold and silicon, or any combination with any proportion of gold and silicon, okay, is always 0. So you have written here XA gold 0 pure. I'm very sorry. I'm very sorry. I'm very sorry. In either case, I should have not written. Yeah, yes, don't rush. I cannot change anymore. It will be clumsy. So A, I have written A and B. It should be instead A is gold and B is silica. Okay. So so this is XAGA0 solid plus XBGB0 solid. This line represents any combination. Always or fall on 0 because both are 0. Okay, this is 0, this is 0 for any values of x and xp. This is 0 on the 0 line. So unmixed line, unmixed solid line here, and what is unmixed liquid line? So let us do the same way. Okay, so remember A is I should write here. A is just I actually drew this A right here. A here right. I'm writing here. That will work here also. A is gold and B is silicon. So this will actually remove confusion. so so this is unmixed solid curve, and this is now what you have to, if this is a solid, liquid has higher free energy because the melting point is actually above this eutectic temperature. So liquid has higher free energy. So as it should be here. So suppose it is here. I have marked this. I have called this actually point A. It is not required, but this point actually. Yes, I have shown this A point A, and this point pure gold liquid, and this other side is pure silicon liquid. So 4 points: gold solid, silicon solid, gold liquid, silicon liquid. Again, you connect these points, then what it will represent? Unmixed liquid, 3 energy of the unmixed liquids. I have plotted what on the y-axis? Integral molar free energy, as I told you. Okay, integral molar free energy. In fact, I will show you what is the GL curve and all this. Okay, so so this is your unmixed liquid. And what is the delta GM? Delta GM is actually, I have drawn this delta GM. Note this time the liquid is not ideal. This is, we have solved the problem last time. You have seen this is actually not an ideal solution. So it is not delta GM ideal. So it will be a diversion from the ideal solution curve. Okay. So this is a kind of curve I have drawn actually. So this is the delta GM. Delta GM liquid, and this is the unmixed liquid. Combine these two, you generate this curve, which is GL. I told you, insist on GL and G solid, and then compare which will be stable, which is lower, which is smaller, or in position wise which is lower, etc. So yes, so for single phase comparison, when two phase coexistence, I asked you to draw a common tangent. Okay, and their coexistence. So this I am not repeating. What I am saying, GL curve. So graphically combine this curve and this curve, and you generate this curve. This is your GL curve. Now there is no G solid because there is no solid solution. This is it was all pure solids, no solid solution. So so you have actually, so solids are clearly shown here. Free energy solid, free energy solid. So and this is actually shows here three phases are coexisting. Which are phases? Liquid, this liquid, eutectic liquid, is saturated with liquid. See, liquid is present. A means gold present, gold solid, silicon solid. Repeat: liquid comprising gold and silicon, and this is a liquid phase composition. This solid gold here, pure solid gold here, pure silicon. So three phases are together here. Here it is the, for example, single phase. Here two phase, and here along this is actually a single unique temperature, three phases coexist. Okay, so okay, so three phases coexist. So if so, very interesting. Three phases coexist. No. So we actually came across one phase will be stable, other phase will be unstable. Liquid alpha. So liquid will be, so suppose liquid is above the solid, then solid will be a stable phase, liquid will be unstable. This is when you compare one of them will be stable. And what is the criterion for two phases two phases to coexist? For two phases to coexist, to be together, what is the criterion? Now there it is not actually above below, which is actually which is higher, which is lower. No, no, no. Upper, which is upper, which is lower, or which has higher value, which has lower value. No, no. They are common tangent. Common tangent giving rise to partial molar free energies must be same. Here even there are two phases, coexistence of two phases, and criterion will be based on partial molar free energies being same in the coexisting phases for either component. It was for two phases. Today, very interesting, this is actually three phases. Three phases together at this temperature. One, two, three. One liquid, two solids. So if three phases, then again you see very interesting. So you have a common tangent. This is a tangent here. See, this is a curve. You draw a tangent. This tangent actually reaching this side, this tangent covering this. So you have this liquid has this partial molar free energy, which is actually pure gold solid, and partial molar silicon, pure gold silicon. So they have the same. So these partial values are given by the intercepts. So this these values, and here that value, and initially they are equal to the pure gold solid and pure silicon solid. So these three have the three phases covering three phases. This common tangent covering which phases? This, and this. Okay. So you have drawn tangent on this curve, but common tangent is actually you need two curves or three curves, but you have only one curve, but others are stationary here, But common tangent gives rise to the intercepts when you actually on this y-axis. Okay, so on this actually this axis, the vertical axis. So here this value, so they are together. So this is about the curve. Now I want to reconcile our result with the findings in this curve, and I am actually kind of giving the data. I'm putting the data onto this curve. So how it is followed? So for example, what is this value? It is 0. This you have to start with you have to consider a certain reference of 0. So what is the gold liquid? 0. So for this, if you recall this side last day, this is delta G0 melting gold is what value for the temperature T, and T is what 636 means this you take T temperature 6686 joule per mole, the last day's value. That means melting means the liquid free energy minus solid free energy. This is for gold. So gold liquid minus solid is this. So liquid has 6686 joule per mole higher than the solid. Solid is 0. So this is 6686 I have given. This is the gold liquid. Likewise the silicon, this one. Silicon melting means solid to liquid. So difference wise it is free energy of liquid minus free energy of solid. So silicon here. So liquid silicon minus solid silicon is this much, and solid silicon is considered 0. So liquid silicon has this value. So this I have actually pointed here, this point. So this free energy is in this scale. This free energy is 6686. That free energy is 31497. Now answer, two answers I will show you. These are the this is actually required for arriving at the answers. Because these values you have seen, these values I have used this. These two values I have used. So these are all done in last class. The answer was question to the A. What is the free energy of eutectic melt relative to unmixed liquid? Answer is 11,300 with negative sign. Means this has a lower free energy than this. Let us see. See what is the free energy? This is the eutectic composition, 0.186. What is the free energy of the liquid melt? This is the cup GL. This is the value. What is that value? What is this value? This value is on the line of this zero line. So this value is 0. So this is I have given here. This point, suppose this point is D and this point is C. So it is actually C is the unmixed. So this one is GC, and this is GD eutectic liquid. This is a liquid free energy, integral molar free energy for the liquid, and at this composition, so D and C is the unmixed. At this composition, for this composition, this one. So this GD minus GC. So this takes the GD, this takes GC. GD minus GC. Answer is minus 11,300. You see, I have marked here how much this is 11,300. This is GD minus GC. GD is 0. It falls on this 0 line. 0 minus, and so this is 11,000. 0 minus 1100, 3,000 is minus 11,300. So makes sense. So and this also this is about this. Okay, so this is so this C has the free energy of molar free energy of 11,300 joule. 11,000. This part is over. About with respect to solid. So with respect to C, this is between this and this. This is unmixed line for liquid unmixed. What is a solid unmixed? This itself solid unmixed. I have given here solid mixed. And this is always 0 because these are actually 0 are the two values that we have started with. Assume these solid values are 0. So it is so they have this combination is 0 for this composition is 0. Any value, any proportion is 0 because it always falls on this line. So 0. So this is 0. And what is this? This remains there. Okay. Here what are the same. This remains same. This same. And that value is what? What value? This value. This value. GD value. What is GD is already I have said that 0. So 0 minus 0. Here actually I have juggled with this. Okay. I have change the rearrange the terms, and as a result this separated. This is the main thing. Free energy question B. Free energy of this is liquid. Otherwise same. These are for liquid solid conflict. This is liquid solution, eutectic solution. Free energy of that relative to two cases. One is relative to unmixed liquid. With that proportion of X silicon is 0.186 and balance is gold, and another is with respect to unmixed solid. So with respect to unmixed solid, what should be the answers and what is the liquid? Follow, this is the total cup corresponding to this composition. What is the value? This one. This falls on this 0. So this GD is 0. So previously it was GC minus GD, but this time GD minus actually this unmixed is this anywhere on this actually, and this same point actually, because this composition for this solid also here. So 0, both are 0. So 0 minus 0 minus 0. So you can say 0 minus 0. I may write that if you are interested. So that helps you. GD. This is actually again right same here, right? GD. This is actually unmixed. This is also falls on this GD actually. GD. Right here additionally this is GD is 0. Right. Sorry. 0 also. As such, GD and GD cancel and becomes 0. but and also the way actually we have assigned values here, this is also is for additional information. 0 minus 0 is 0, and this actually I have done 0 plus 0 because of some certain okay alterations in the expressions. Actually, this is actually, see, these minus some terms I have taken to this side and plus one term of this side of this side goes to the other side. Okay, like this side means this is this. So one term on the second term, first term of the okay this okay, what should I say? Because first term of the second term, first of the second term, us has taken to the side. This has second of the second first parent is what is this called? First round bracket and square bracket and second square bracket. The second term in the second square bracket has been taken to the left hand side in the okay left hand, okay this side, and brought together with this one, and this one the second of the first square bracket goes to the goes to the actually goes with this goes to the this one has gone where here no this has gone this is there, and this is actually that's juggling actually this uh, x silicon or x silicon in common actually. It is better to say this x silicon common, x silicon taken common with plus sign, x silicon together, and x gold together, then plus. So if we apply this, you get 0 is 0 plus 0 is 0. Here you can say 0 minus 0 is 0, or simply in each case gd minus gd is 0. So this is about the second problem. I think this problem is this additional thing. This was not asked in the problem. Graphical representation in addition to our to this okay, numerical solution, we have seen here. We have taken up this exercise, and we have actually very satisfactorily shown this with the help of a clean energy composition diagram, so that we are now more confident about this. Okay, and one additional thing that you can say for eutectic diagram, for the eutectic situation we have not drawn before this free energy composition diagram. So this is actually gives us a good practice how to draw free energy composition diagram when it at the eutectic temperature, and this is actually very nice diagram. So this is the free energy composition, and you have this. Okay, this is three things, connects three things: liquid and two solids in equilibrium and together. So this is over. So let me do. I will take up now problem 3. So without wasting time, so let me remove the problem 2 is over. So remove this, remove everything. Problem 3 will be discussed only. Okay. So good idea if I remove this. Problem 2 out, out, out. Everything is out. Okay. It is better actually since I have some space here. Problem 2 is also, in case you are interested, problem solution 3. Problem 3 now. Problem 3 is last one, last but one. Another still another problem we'll take up. So problem 3 and solution. Solution. Not bad if I remove this diagram. Okay, remove this diagram. So problem 3 says what? Problem 3 says, see, this is about cerium graphical representation. It says, okay, problem 3. This is unnecessary. Now remove this. Only problem 3 remains. Okay, you see. Okay. Problem 3 solution. Right. What is the problem? Let us read on. Cesium and rubidium form complete ranges of solid and liquid solutions, and a minimum occurs in the solution in the solidus and liquidus cups. In the solidus and liquidus cups, at x cesium is 0.5, and when means x rubidium is also 0.5. Temperature and temperature 282 Kelvin. If it is assumed that the liquid solutions are ideal, calculate the integral molar free energy of mixing uh, of solid cesium and rubium. Both are solid actually. Solid cesium and solid rubium to form the solid solution. So to find the free energy of mixing, okay, that is solution free energy minus unmixed, that value. You know the free energy of mixing, very popular term, to form the solid solution of against that composition of x cesium is 0.5 and the same temperature of 282 Kelvin. So first of all, let us draw the diagram so that we have a idea of the problem. Let us start. This is draw this. This is your cesium. This is what x rubidium Rb. This moves from 0 to 1. When it is 0, it is cesium, and when it is 1, it is rubidium. This is your okay, and the diagram is, suppose this is the 0.5 as it should be. So this is not bad. The diagram is like this. This is the your diagram. Okay. This is the liquid solution, which is ideal. Ideal. This is the temperature. Temperature. Okay. What temperature it is? This is your okay. 28. This temperature is minima. Where minima occurs? 282 Kelvin. And these temperatures are also, see, melting point is, this melting point of cesium is 302.8. It's not, I'll write here. And data given. The melting point of enthalpy of melting. This is for cesium. For cesium, enthalpy of melting is what? 2090 joule. and melting point is 302.8 Kelvin, and for rubidium, delta H0 melting, enthalpy of melting under standard state is 2197 joule, and the melting point is slightly greater, 312 Kelvin. And so this is 312, you may write this, not bad, Kelvin, you may write. This is 302.8. 302.8 Kelvin. Our problem is about 282 Kelvin, where the minima occurs. There is a minima. This is the minima. Question is this about P energy of mixing. What is this? P energy, calculate P energy of mixing of solid cesium and solid rubidium to form solid solution. So this is liquid. So if you write here, this is the solid solution. This is the alpha, solid solution. And this is a very little bit peculiar diagram. Solid solution. Okay, liquid and liquid solution and solid solutions. Okay, it is not isomorphous, but it has some similarity with isomorphous diagram. So this is actually liquid plus alpha, both sides. You don't have this. You have to understand. There is no beta like eutectic. No, liquid plus alpha, liquid plus beta. No, alpha either side, because liquid plus alpha. Both sides is liquid plus alpha. So this is how many minutes it is? Okay, is okay. So this is your diagram. This is it. So find this. As it is asked, so write this delta for what is the write the reaction. Okay, so to find delta Gm, it is better write what is to be found to find delta Gm for the process is what? XCS solid plus XCD RB solid rubidium goes to what? Goes to 1 mole, is 1 mole of what? This cesium rubidium 1 mole cesium rubidium, yes, cesium rubidium solid solution, solid solution. No problem, no problem. So let us try. Let us I remove this line. So what is this delta Gm? To find this difference, the delta G of this reaction is the delta Gm, because this is a mixing process. This is a mixing process. So delta G of this minus G of this together is unmixed. Solution state means mixed state minus unmixed is the delta Gm. You remember this. So delta Gm for this. What is this? Shall I write here? Delta Gm is write this nicely. You recall this. This is what? X say Ga bar m plus xb Gb bar m. I am writing this in terms of A and B. Okay. So X. So it is better actually write X Cs G. I'm writing for you. Okay, what is this? Remember, XCS plus XRB is 1. XRB is what? How much it is? Oh, I forgot to write this. This value is how much? 0.5. Sorry, write this. 0.5 plus 0.5 is 1. X is what it is? I am writing for you again. XCS, what is this? Right hand side is what? GCS bar minus X plus what? X rubidium. This was already discussed when you started solution, but I am writing once more. This is the right hand side minus left hand side. Left hand side is what? X CS again. GCS, this time this not in the solution state but is a pure solid. GS 0 plus X RB G RB 0. So what you get out of this? XCS, if you take common actually, XCS common, then GCS bar minus GCS 0, likewise plus XRB in common, you have GRB bar rubidium minus rubidium pure means standard. GI bar minus GI 0 is what? RT-ln activity. Recall this. So XCS times RT-ln activity of, oh, you write better. It is, I should write somewhere actually. Where should I write this? This is actually, this is solution. CS solid. Okay, this is actually pure solid. These are solids. So CS bar minus activity of cesium. So with respect to solid. So I tell you what, it is better actually. I am writing because to avoid any confusion, I am writing here additionally solid. This solid, this solid minus this solid and this solid. So rubium, what should I write here? X0 solid additionally, maybe additionally. So solid. So now if you put that, then it will be easier for you to understand. And write here G0 is solid. Remember, GI bar minus GI 0. GI bar minus GI 0 is RT-ln activity of this with respect to this. Right, this minus this standard with respect to this standard. What is that? Solid standard. So what should you write here? Activity of cesium here with respect to solid standard. Solid cesium as standard state. Likewise, other side, second term, rubidium times RT-ln activity of rubidium with respect to solid rubidium as standard state, not liquid. The question is, if it were with respect to liquid, you would get the answer easily, because it has been said that the liquid solutions are ideal. Liquid solutions are ideal. So what is the activity for ideal solutions? Mole fraction. A mole fraction is given. So very easy, but it is not difficult either. So knowing the activity of a component with respect to one standard state helps you to find the activity of the same component with respect to any other standard state, provided you know the standard state change in standard state value from one to the other, which you know here. Well, from this data you will find this. Okay, so let me move on. Remove this. This is all over. So you see, I'm trying to find out these two data: RT-ln activity of cesium and RT with respect to solid cesium standard state plus RT-ln activity rubidium solid. with respect to means solid rubium standard state. So for this, I know what we know easily what RTLN. Let me write this. I'm writing you now. Just change the context as well. Remember, this is our focus. Find, find, and substitute back into this. Call it equation one. It will help you. Okay. Now we know RTLN one by one. Take up cesium first. RTLN activity of cesium solid is what, recall this. Recall, actually should have written yourself. It is actually delta G0 melting. Okay. If solid left hand side, it is delta G0 melting. If liquid is left hand side, is minus delta G0 melting. But I'll show you again once more. So G0 cesium liquid minus G0 cesium solid. It is delta G0 melting of cesium. So this equal give in bracket, this square bracket, plus RTLN activity of cesium liquid. See, clear? So from what you get this? Gi bar is Gi bar. So Gi0, so Gi, see, follow, Gi bar is Gi bar. Identity. Gi0 plus RTLN 0, see, liquid standard state plus RTLN activity of cesium with respect to liquid standard state. This together. And this minus take to this side. Again, taken to this side, it is G0 cesium solid. Gi0 plus RTLN activity of cesium with respect to solid cesium standard state. So recall this. I should not. I often I write this Gi bar is Gi bar. Is Gi0 1 standard state 1. It is here maybe solid plus RTLN activity of I with respect to the standard state 1 is what this is left hand side. Right hand side is what? Okay. Right hand side is what? Actually, I should write this. I will remove this line. Okay. Is what? Right? Gi0 quickly. Gi0 second standard state plus RTLN activity of I with respect to activity with respect to what? Good question. Always you ask yourself, activity with respect to what standard state? So standard state 2. So these I have used. This I have actually manipulated and I have got this. Okay. So this so for cesium. Okay. And standard state 1 is solid maybe and standard state 2 is liquid. It can be Raoultian and Henryan. So same. So given to you this one, let me know, otherwise it is not interfering with our okay presentation here. So it will not clear. Okay. So what is this? This is known as tell me delta G0 melting. Delta G0 melting of cesium. I am currently talking of cesium only in the cesium. Melting of cesium. How will you get this? From this data. What is delta G0 melting? Tell me. Delta G0 melting of cesium. Okay. This I'm writing you. Delta H0 melting. Delta H0 melting is what? Delta H0 melting 1 minus number of times I have T by Tm. Melting cesium, right here, cesium. Plus what is this? What is activity of cesium liquid? Fortunately this, see, what is your strength? What do you count on? Now you know this value. Hence you know this unknown. This is to be plugged into here. But this you don't know. But since you know, hook up this with this through this relation. This is called change of standard state. Starting from Gi bar is Gi bar, etc. Always. Why it is and how it is known? Because this is ideal solution. Ideal solution means, tell me what? X, CS, activity is mole fraction. So what is that value? Still that value, what is the liquid composition here? All this composition is point, or liquid is 0.5 mole fraction of rubidium or cesium, and solid alpha is also 0.5. This point. You are asked at this. Go see the question. Calculate the integral mole of pH of mixing of here. So see what are the things content here. You can see. See this is also solid solution. Okay. So, mixing of to form in solid solution. This is also solid solution. Yeah, this is pure solids. This is the solution solution, and the impure state. So plus write this x here, x is 0.5. So RT ln 0.5. Will you? So what is this? Then you'll get this. Okay. Let me write this. Okay. This data I tell you. This is actually what is this? Delta H0 melting. You see, write this 20. Write this one line. Cesium first 2090. 1 minus T is hot temperature. You are talking about 282. What is the melting point? 302.8. Happy? Oh, sorry. Plus RT ln 0.5. R is 8.314. T is 282. Ln 0.5. So what you are getting from this? Okay, if you do this correctly, you get actually all figures. You do yourself. I'm giving you 140. This you get. This side you get what? 143.6. 143.6, and this term will be negative, obviously. 1 minus 16.25 plus minus 16, sorry, so 1625, 1625. This is okay. This is this. So gives minus 1481 joule. This one, okay, or TLN activity. So you will use this value here. So save this. Call it 2. This value will go where? Here. Similarly, find out this one, arterial, and similarly, arterial activity rubium. Similarly, then that value will go there. And XCS, XRB both are 0.5. So, get the answer. You'll get the answer. So, similarly, quickly I am writing. Similarly, RTLN, this term, activity of rubium solid, rubidium solid, rubidium, this one. Solid is what? Similarly, write here delta H0. Don't have to write actually this line. I'm omitting. Same, okay. Actually, I'm writing for you. Delta G0 melting of rubidium, this term, plus RTLN activity of rubidium liquid. Okay. This delta G0 melting is what? Right? Delta H0 melting rubidium. Be like this. Instead of cesium, 1 minus T by T melting rubidium. This term plus RTLN. Here you write activity is nothing but XB. XB means, B is here rubidium. And what is that value? It is 0.5. So it is also 0.5. So write here RTLN 0.5. Just D2. So what you are getting? Delta H0 melting is what? I'm writing here, this side. Delta H0 melting is what? Here I write 2197. 1 minus T is what? 282. 282 over TM rubidium is 312 plus RT means 8.314, temperature is 282, ln 0.5. This term is same. This term remains same. So the answer is minus 1625. So what is this value? This value, if you try this value, 211.3, and this value will be, as I told you, minus 1625 like last time, plus minus 1625. How much it is coming? 1414. Okay, like this. Okay, it is 1413. Okay, this 211.3 minus 1625, it is 1413 in joule. So this is 1481. Call it 3, equation 3. So one our main equation, source equation is 1, from 1, 2 and 3. So from 1, huh, write better, substituting. Acha, it is better, right? So you don't have to. From 1 to n, you will understand this. From 1, 2 and 3, what you get? Write this delta Gm, right? Delta Gm is what you write, cesium is what, cesium, right? Once more, right? Times RT ln activity of cesium with respect to solid standard state, plus x rubidium times RT ln activity of rubidium with respect to solid standard state. Is these values are known now? One is xch is 0.5 times what value? RT ln cesium solid. This value is from 21481, negative sign, plus 0.5. What is the value of RT ln activity of rubidium solid standard state? Is what is this value? Value here minus 1413. So it comes down to this value of minus 1447 joule. Okay, delta G. This is integral molar, so per mole you can write or answer. Write mole, answer. So with this you have completed problem 3. So this, okay, no problem. Next I will take up problem 4. So problem 4 is better I write actually this side. Yeah, I remove this figure. Yeah? This is this one. Okay, problem 4. I will draw the diagram also. Problem 4. What should I write? Let us remove this few lines. Okay, this is not. I'll draw a diagram. Problem 4. Start. What is the problem and the last problem? This is again taken from the same source. This is from second edition, Thermodynamics of Materials, Introduction to Thermodynamics of Material. I'm sorry. Introduction to Metallurgical Thermodynamics, second edition by D.R. Gaskell. This page same, 408. So problem 4, source D.R. Gaskell. Same reference. D.R. Gaskell. Problem 4 is what it says, this problem. FeO and MnO. FeO and MnO form ideal liquid and solid solutions. Ideal liquid. So we are actually discussing assignment number 12. This is the last problem. Ideal liquid and solid solutions. solid solutions. Okay, calculate the temperature. Calculate the temperature at which equilibrium melting begins. At which equilibrium melting begins. In solid and liquid will coexist actually. That is equilibrium melting. That temperature. That is the that is actually the temperature actually. You can write melting begins, no problem. Yeah, on actual solid and liquid. That is at the melting point. Equilibrium melting means melting at melting point. Melting at melting point is equilibrium melting. So begins. So this in which equilibrium when the equimolar solid solution is heated. Is heated. Calculate the composition of the first form liquid. First form liquid and the temperature at which equilibrium melting is complete. Is complete. I'm and this I am adding and find the and calculate this I am adding actually. Uh, so four questions actually and calculate the composition of the last form. This is first form. This is last form solid. These are liquids are solid. These are actually solids and first form and lateral solid. This is the question. This is the question. So there are actually say four segments. First important is find the calculate the temperature. Actually, let me draw the diagram that will help you. This is the solution. Solution just below solution. Let me draw the diagram. Again, draw same way. This is very easy isomorphous system. Both liquid and solid are ideal. So what is this? Okay. Like this is so liquid. This is right here XFEO moving this direction 0 to 1. This is MNO This is FeO itself. This is 0.5 equimolar, 0.5, mark that 0.5. This is liquid phase, liquid solution. This is alpha solid solution. Both are ideal, but question is about this composition. Let us see. You're hitting here. Means until this point, this temperature, this is solid. Now actually, this is what liquid plus alpha, right? Liquid plus alpha. So what will happen here? Okay. So you have to find this temperature at which the melting will begin. Until this temperature, it is solid. Then it will begin and liquid will start coming out, and then proportion of solid will decrease and liquid will gradually increase when it will be here all liquid. I am showing you is all liquid. It is the commencement of the melting. This is the completion of melting. When commencement, this temperature you have to find, right? This T temperature is this side. Some data are giving. Data giving is these melting points are giving. Like this. This I'll give you. These melting points are actually 1643. This side FeO. This is a Kelvin, and MnO has a higher melting point 2148. So question is what temperature will be this? And when this 0.5, you don't, you know this is the composition of the alpha solid solution. What is the moment liquid starts forming upon melting? What is the composition it will come? You know very well that this is the composition of the liquid, fast form liquid, solid fast form liquid. As we increase the temperature, liquid composition will vary, will change along the liquidus. We call it liquidus. This is solidus, and solid composition will change along the solidus. So, for example, if we increase the temperature here, then liquid solution will have this composition, which will be actually more enriched with MnO or less enriched with FeO. Less, like compared to this, less enriched with respect to FeO. And the solid will be, this is a liquid, solid will be opposite. Here it is more enriched, and here it is yes, it is here actually opposite means, see, let us see, yes, solid liquid has no liquid is here, liquid here and here, it is less enriched with FeO, more enriched here. Okay, that means when it is increase the temperature, liquid is less enriched with FeO, more enriched with MnO, more, and this solid will happen here. Solid will be solid also alpha. Only thing is happening in, I'm sorry, solid, okay, solid also. See here it is this one compared to this it is more enriched. Compared to this, is more enriched with MnO. That happens, but what changes will make that liquid, and as we increase the temperature, liquid proportion, percentage liquid will increase and percentage solid will decrease, and when you will reach here, the solid alpha will disappear and it will be full liquid. This is the end of the melting. So I'm sorry, okay. So anyhow, and this can be obtained of the proportion of liquid and alpha from the lever rule. So these I'm not discussing. This is additional discussion, unnecessary. Yeah. So concentrate. Two things to be found. I am encircling this. What is this value? Hot temperature. That which this melting, it is equilibrium melting. It is called. If it was actually, it is under equilibrium condition. You have actually increasing here. This is actually where actually liquid and alpha coexist. So this, so alpha and liquid will coexist. So equilibrium melting is here, or say melting, simply melting. Melting will start. Comments here at this time. So what temperature? This is one question. What is the fast form liquid? Composition will move to this side. Corresponding to this step, what is the composition of liquid? This. Calculate, calculate. Two segments. And the last one, the temperature at which equilibrium melting is complete, means this temperature. I am just showing you this temperature. I am not showing this temperature you have to find. And what is the what I have added? What is the composition? This is not in the giving the Gaskell's problem, but what is the composition of the last form solid? The solid composition moves along the solid earth. So when last form solid has the which composition? It is starting composition is 0.5, moves up. This. What is this value? What is this value? This we know. This side liquid composition, here liquid composition we know 0.5. And here at the beginning we know the solid composition 0.5. Now I tell you what, how to get this value. So these two. See, this is a two unknowns. Temperature is unknown. So you just consider the commencement of the melting. Commencement of melting, not the end of the melting. That will take up at the end. Or I will give you actually outline, and you will actually in the same manner you will solve actually the okay same manner as we solve the first part. The same manner you solve the second part. So concentrate on this question: what temperature it is, what composition of the liquid solution, first form liquid. These two questions we are going to solve. So with some data, it is a good idea to write this data given. APO, for APO, so right here, for APO, delta H0 melting, which is better, I write, right, right here. For APO, right, little, this delta important. Delta H0 melting, how much it is? 30,960 joules. How much it is? It is 1 hour 8 minutes. 8 minutes. 1 hour 8 minutes. Okay. Okay. Melting is how much? What is the data? 30,960. 30,960 joule. What is the melting point? You already see there. What is the melting point APO? This side 1643 Kelvin. For MNO, delta H0 melting is how much? 54,400 joule. And melting point is what? 2148 Kelvin. This is data given. Okay, start solving. I ask you, see, you actually use that one. See, follow this. You write RT ln. See, you know the activity. See here, what is the composition of the liquid solid? Here, composition of solid is known. Is it alpha, alpha? All alpha. 0.5. What is the coexisting liquid composition? This one. Achha, that means since it is an ideal solution, this alpha is an ideal solution, you know the composition of the solid solution, alpha. Composition of the or XAPO, for example. XAPO you know, or XMNO also you know. Then what you know, what else you know? Knowing that this is an ideal solution, you know the activity. Because for ideal solutions, activity is mole fraction. So activity of this solid solution at this point you know. Using this, exploit this to know the activity of the coexisting activity of FeO liquid. Sorry, activity of FeO solid means in the alpha phase, you know, is the mole fraction, is the 0.5, 0.5 actually. What is the activity of FeO liquid? Activity of FeO liquid here. With respect to liquid, pure liquid as the standard state. That is the meaning of this activity of FeO liquid. You know, as I told you, if you know activity with respect to one standard state, which is solid here, you know the activity with respect to another standard state, liquid here, which you don't know, but you will find utilizing this one. And this not only for FeO, for MNO you can do this. If you can do this and generate two equations, then you can solve one unknown, two unknowns. You require two equations. One equation will not be enough. Two things, calculate two things. Calculate the temperature, one, calculate the composition of the first form liquid, two. So two equations for each. For FeO, say we have, okay, I start RTLN, activity of FeO liquid, which is unknown for you, which you will find. Okay, you see, you follow me. Okay, activity FeO liquid you will find. Then this activity of FeO liquid, which is a solid solution, which is an ideal solution, will be XFeO liquid. Similarly, if I try with MNO, then you will find XMNO liquid, some value. Knowing XMNO solid, which is solid solution, and which is ideal solution, solid solution means you know the composition. If you follow this, then what I am giving the plan and the total plan. Recipe. So XFeO liquid, some function of temperature, or an expression, say value or expression, XMNO. Then, but they are bound. They are bound by equation. What is the bound? XMNO and XFeO, they together is one. Perhaps this will give us some lead and some clue to solve the problem. So start. RTLN activity FeO liquid I am writing. A moment ago I did not write that. Okay, you know, delta G0 melting. If you liquid this side, then delta G0, liquid minus solid. Okay, solid minus liquid, so minus which you know. Okay, it's okay. Let it be. Delta G0. Which one you want? Okay. Well, until active solid, maybe since I know this, I write this, say for example, solid means alpha. Solid is right here. It's alpha. Alpha solid solution. Activity of FeO in alpha solid solution. Is okay. Is okay. At a solid solution. If this, then what you write here? You wrote a solid this side, left hand side, then it will be delta G0 melting FeO only. If liquid left hand side and solid the other side, then it will be minus delta G0 melting. This you can check actually. So solid left hand side, and other term what it will be? RT ln activity FeO, the other standard state liquid. This is unknown. This is the unknown stuff. This is the known stuff. Okay. L is the liquid solution. L is the liquid. It is alpha solid solution. This is liquid solution. This is solid solution. This is liquid solution. This is alpha. alpha solid solution. Okay. So anyway, what is this value? Keep on writing or write as much as you can write actually RT. R is 8.314. Okay. I'll write later. RT ln activity of APO is what? Solid. In the solid solution activity of APO, solid is what? Nothing but XAPO. XAPO. Okay. What is this value? XAPO in the alpha in the solid solution is what? Delta G melting is what? As I told you, this is standard delta G H0 melting APO 1 minus T by Tm APO. I remind you one thing, that this relation is valid under the consideration of delta Cp is 0 for the melting process. Delta Cp for the melting means Cp of liquid minus Cp of solid is is approximately 0, is negligible. Then otherwise delta, this is under that condition delta H0 is independent of temperature. Delta H0 melting or delta S0 melting, Kirchhoff's equation. So remember that. But anyway, plus RT right here, R T T is unknown. Remember, T is unknown. Activity of APO liquid is what? XAPO. Write this XAPO liquid right here. Here XAPO solid right. You have the some okay clarity in expressions. Oh, sorry. XAPO. Quickly do this. Huh? What? All right. 8.314 T ln XAPO is how much? XAPO in the solid phase means alpha solid solution is 0.5. So it is 0.5 here. What is in the liquid? Coexisting. What is XAPO here? Here 0.5 here in the liquid. This is the question. And not only that, temperature is what temperature this is happening. Twin question. So you let us proceed. So XAPO is what? ln 0.5. ln 0.5. Okay, is what? Delta H melting is given here. Say for APOC 3960. 1 minus T is the unknown. T is the unknown this time. TMAPO, melting point of APO is what? 1643. 1643 Kelvin. Plus RT right here, 8.314. T, oh, sorry. It is RT ln XAPO. RT XAPO, oh, so very bad. ln, please correct this. Hey, this ln. RT, ln, activity is mole fraction for ideal solution, which is given here. Both liquid and alpha solid solution and solid solution both are ideal. So ln XAPO, RT ln XAPO. This is the question. What is XAPO? So right here, am I right? This is unknown. This question is unknown. This is unknown. Two unknown. This temperature is unknown. This composition is unknown. So T unknown, XAPO unknown. But you see this side XAPO is known. 0.5. So just simplify. If you do this, or you can do yourself also. Let's see if I can help you. This is actually, I tell you what, it is minus. Okay, shall you write another letter? Right here minus 5.760 minus 5.76 T. This is what if you write this 5. Okay, very good. Is okay. 960 minus 18.843 plus 8.314 T ln XATO. You write here, you may write this liquid, XATO liquid, maybe no, not bad. Very good, in fact. Very good. XATO liquid. Like this. XATO liquid, XATO liquid. Okay. Temperature is unknown. Okay. Very good. So you are very close to the analysis of this part. What is this next is or side change or do this or minus 5.76 T, okay, minus 30,960 plus 18.84 T is what? 8.314 T ln XATO liquid. Okay. Correct. Okay. Or XATO liquid is right, or XATO liquid is what? If you do this correctly, exponential minus 3724 by T plus 1.57. 1.57. Okay. 1.57. Call it equation 1. Perhaps. Yeah, have I equation 1. Box this box. Equation 1. So now take up the next. Similarly, you write yourself. Okay. RTLN. You do write this. Manganese with respect to manganese. Manganese oxide. I mean RTLN, activity of manganese oxide solid. Here instead of FeO write manganese solid, means delta G0 melting MnO plus RT ln A MnO liquid. Happy? Okay, this is liquid solution, this is solid solution. Okay, this is solid solution, this is liquid solution. Okay, liquid solution. This is alpha, solid solution. So let us not waste time. Remove this. This problem is already over. This is, I mean, problem 3 is over. Problem 3, actually problem 4 is there, no? Remove this. Sorry. So problem 3 is already over. Problem 4. Problem 4, the ongoing problem. Problem 4. So similarly, just proceed similarly, or R3 ln, this is XMNO solid in the solid phase, 0.5 FeO XAPO is 0.5, XMNO is also 0.5, equimolar. Or 0.5 means it is 0.5, other is 1 minus 0.5 is 0.5. Together is 1. XMNO solid is delta H0, write this. Delta H0 melting MNO, write this. 1 minus T over Tm MNO. In terms of MNO, I am writing. Instead of FPO, I am writing MNO. Okay. T minus 1 minus plus RTLN. What will I write here? Since ideal solution, X MNO like this, X MNO liquid, and this we don't know. This we have to find. XAPO you have to find means XMNO you have to find. Either one you know, the other you know. But in any case, unknown. In any case, this is unknown, this is also unknown. Or this is 1 minus XAPO. That is possible also. But anyway, keep it in this form. Or quickly, or right here. Just copy here. 8.314 T ln 0.5 ln 0.5. This is delta H0 melting of MNO 54,400. 1 minus T over Tm melting is how much? 2148 plus R is what? 8.314 T ln X MNO liquid. No way. Keep it there. Now take this the other side, only keep this other side. Or next is what? Right? This is nothing but minus 5.760. Good. This is what? 54,400. This is 1. And then what it is? Let me check actually. 54,400 minus 25.32. 25.32 T. This is over minus plus 8.314 T ln X MNO liquid. Or will you actually little bit or last? Okay. Okay, last phase of rearrangement. Okay, just keep this. Okay, just write this. Follow this. Okay, this here. Take this all to the left hand side. What you are getting? Minus where am I standing here? Here, right here. Yeah, like here. Minus 5.760 minus 54,400 to the left hand side plus 25.32 T equals to 8.314 T ln X MNO liquid. Happy? Or X MNO liquid is what? X MNO liquid is what? Like in this format, okay, you know, it will be exponential. Why exponential? Because it is a log XAPO. If you want to strip the log ln, then it will give rise to exponential. On the other side, exponential is what it is. It is so exponential, right? Minus 6543 by T. Minus 64543 by T. Minus 6543 by T plus 2.3 plus 2.35. Again, box this Call it equation 2. I am removing this first line here only. You have XFeO liquid, XMNO liquid as a function of temperature, as a function of temperature. How you solve? You solve because there is a weakness of these two terms, that they together is one. So you don't want two unknown. You want to get an equation in terms of one unknown, say temperature. So these two are related, mutually related. What is it? Since star, because XFeO is 1 minus XMNO. So what we can write? Second line remove MNO. Okay. What you get? XFeO is what? Exponential XFeO is 1 minus, so XFeO liquid is what? Exponential minus 3724 over T plus 1.57 is nothing. 1 minus, again exponential, in bracket, XMNO is what? Liquid is what? We write here XFeO liquid is, we write this, write this, no problem. Or if you don't write, it is implied. So exponential what? Write this nicely. Okay. What is this? Minus 6543 over T plus 2.35. How to solve this? This is not easy, non-linear. Yeah, so this actually we have to solve by trial and error, iterating method. So solving by trial and error, I did myself this way. Solving by trial and error. I tried myself actually this way. I would consider this. Okay, any trial and error. The starting value I considered 1896 Kelvin. Okay, how I got this actually from this somewhere actually. See. Okay, anyway, let it be. The answer is T will be found as, or if you have any other method, so numerical analysis method, you try to solve this. T will be, answer is 1891 Kelvin. This I got actually, but 1889 Kelvin. Okay, it's okay. It's okay. So this is answer. This you try. Okay, this you try. Actually, there are methods of trying this. Actually, you may first consider suppress this. This may be possible. Suppress this. Just here, try to find what is the value of T. Value of T. Then what we'll do? Next time you'll do, put the value of T into this, and now consider. Second attempt, consider. Put that value of T that you get in the first attempt here, and one intact. Find what is this T. Treating this as an unknown, what value? This is the first iteration. Then again put that new value of t into this with this and find this odd value. Then as they close up to each other, then actually you will see I tried this. These are the different types of values I start with. Start t is this is my method, my result. T is what I start with 18 perhaps from this paragraph. This 1896. The suppress one and get t, and that is the starting. That will be recycled and recycled. That will be recycled, and then again new value will emerge. Recycle, again recycle. Start since 1896 Kelvin. That I got from this. Suppressing this altogether, I get T. Then what values continuously I get, I tell you what. See, gradually you see, I am giving you. 1896, okay, 1897, 1900. 1896, then what is the actual answer is, I have given answer 1889. 1896, then 1885, next, I should not go there. Actually, I am writing here since I don't need. This equation should be 18, 1893, 1885, then 1897. This may happen. Decrease, then again increase. 1897, then 1883, then 1900, 1900. Then perhaps there is a stop there, I see. 1900. 80, 89, 1890, 1889, 1889, like this, okay. Actually, 1891, I'm writing. 91, 1890.5. To try yourself. Then they're closing up now. Now on iteration you are getting back almost same value. Means this is the answer. Here actual gap, huge gap. These are not reliable. This is reliable. So 1991, 90.5. So actual answer is 1889 Kelvin. Okay. And second part is what? What is the composition? What is this value? What is the XAPO liquid here? Liquid of the liquid solution. XAPL is what? Equation. This is the equation. And from equation 1, XAPO liquid is what? Now you substitute this value here. Answer. So remember this 0.5. It should be anywhere between 0.5 and 1. But means it will be greater than 0.5. Let us see what value it is. Answer is 0.67. 0.67. Again answer. 2 out. Then over. Problem is over. This actually the remaining two parts. The remaining two calculations remaining two calculations are for you to try. You try yourself. So same logic, same. But I'm just giving answer. Answer I'm giving. Answers. And this is over. Answers given. What temperature? Guess what temperature? Guess. Go up here. This will be. This cannot exceed to 148, and this will be greater than this. Somewhere between this, okay, and above this temperature also. What temperature? 1889. Answer is T is. You try yourself. For T is what value? 1973. 1973 Kelvin. And another is XAPO is what? Tell me. Guess. Guess. See here. This one must be less than 0.5. Repeat. Go here. Melting is complete. Oh, sorry. RT, LN, XFU. Okay, sorry. I should have not done this. Okay. Yeah, you see this one. This is the temperature. This is the composition XFU. Now this time which composition? Solid. This is the liquid composition. This is the here liquid composition is not 0.5. 0.5. This 0.5 goes here. Liquid is 0.5. Corresponding solid. Accompanying solid is what? Should be less than 0.5 this side. 0.5. What answer it is? 0.342. Try yourself. Try yourself. I tell you, clue. You just go there. Again here. Say where I wrote actually. Where I wrote. Suppose here. Suppose I am showing the second one. You write the similar one. Right? What you know this time? This time opposite will happen because activity of XMNO liquid you unknown, but you substitute what? Liquid XMNO liquid is 0.5, and this you don't write 0.5. You write XMNO solid. Similarly with APO. Similarly, activity of APO solid you don't know, right? Keep it there intact, and APO liquid, you know, APO liquid is the same composition is the 0.5. Liquid composition, you know, 0.5, and ideal solution. And here this will be delta zero melting for MNO. Okay, see, this is also MNO, you know, actually. These data are given there. Okay, see, this part is no problem. This part is no problem. Okay, this part, and APO also similarly you did APO. Okay, in the solution already discussed, so you have no problem. So the delta melting is okay, remains there. It remains there. So what will happen? Only thing which will happen is switch. This is known in this case. This is unknown in the case we discussed. This we have solved. Treating this as unknown because activity is a mole fraction, ideal solution, but unknown. But in this case, XMNO will be known. And other side, here it was known, MNO solid was known, this will be treated as unknown. This is about MNO. APO similarly, then generate the equation like this and this. Then this will be what? XMNO solid. This will be XAPO solid. Then they are hooked by XAPO solid is 1 minus XMNO solid. So these exponential two relations and solve trial and error. Answer and substitute. This is actually XAPO. This is remember XAPO is what? Second part is actually I am writing you. I have written where answer I have given. Liquid I have given, so it is better I write here solid. Is it XAPO solid? Solid. This one. This temperature is unknown. This composition is unknown. this composition is known. Like here in the problem that we solve, the two parts we solve, this composition, liquid composition is known, solid, I am sorry, solid composition is known, liquid unknown. Here liquid composition is known, see here this, here this, here this unknown, this unknown. This is the last form solid composition. So thank you very much. With this actually we have solved all four problems dealing with related to phase diagram. We will now take up a new chapter, altogether new chapter, that is the Gibbs phase rule. That will start now. Okay. So is that okay? Okay. So I am just removing everything. Assignment 12 over. Okay. Which one I will remove this? I can remove this. Start problem 4. Right. This solution. Oh, solution thermodynamics also over. Solution thermodynamics also over. We may later come back with aqua solution, that is regarding electrolysis and okay, aqua solutions, okay, and half cell potentials, the aqua space may come. But this solution thermodynamics that we have been discussing. 47 minutes gone to. So in right time, 30 minutes, but no problem. We are free actually. Just we are passing time. Okay. So this is solution thermodynamics. Actually, this metallic solution that we have considered often. Okay, and solution properties, what not, model, regular solution, model, alternative standard state, interaction coefficients, and what alternative standard states and interaction coefficients and problems all dealing with this. Okay, so solution thermodynamics also done. Hang on. This actually the Gibbs phase rule. I want to start because actually it is a lot of discussions there. Gibbs phase rule, derivation, that will take up first, and then what we will do. So solution thermodynamics over, assignment 12 over, and more importantly solution thermodynamics over. So we'll start this. Okay. So thank you. So Gibbs phase rule, I tell you that it actually the Gibbs phase rule is is about finding the number of variables, finding the number of variables to describe the system, state of a system at equilibrium. This is in short. Finding the number of, well, if I may qualify it, number of independent variables. We will never consider dependent variables. Independent variables. So number of independent variables to describe the state of a system at equilibrium. This is what the Gibbs phase rule is all about. That is, this is called degree of freedom. The degree of freedom, the degrees of freedom, F, and it has a fancy relationship. It will emerge with come up with relation of degree of freedom involving number of components and number of pieces. That derivation, a little bit lengthy, but very interesting. And this Gibbs phase rule is very useful, very interesting, and very important. Okay, and in this connection, we will also learn how to draw stability diagrams, which we actually use. What is that called? Softwares, Access, okay, or other okay softwares, thermocal. Phase diagram is also actually kind of stability diagram. Now, first of all, we will not go actually about this one. The application that where we apply Gibbs phase rule. So that is actually in the stability diagram, in the phase diagram, okay, etc. That I will mention. But Gibbs phase rule. So start. I repeat what I said. Just the number of, for example, let me write. Let me write. The Gibbs phase rule. Totally a new chapter in our thermodynamic life. A new chapter, new episode, new solution thermodynamics over. Okay, this is the Gibbs phase rule. We'll discuss for a number of classes. We'll take up number of classes to discuss this because first of all, the derivation will require some time. Then explanations, applications. Okay, make use of the Gibbs phase rule. Okay, so I tell you one thing. Remember this. Short. At the very beginning lecture, first day or second day, when I said state functions, what I said, this state is a function of, I say, the independent variables. Variables, but independent. Right hand side is y is independent variables. State is function of state functions. These are called state functions, on which the state of a system is dependent. State is state of a system. State of a system is function independent. No dependent. Okay. Like say, see, mutually independent variables. The temperature, pressure, mass. Okay, like this. Okay. Function of independent variables. Or even easier example. Well, if you ask me, why sir you are writing this? This is your degree of freedom. This is your Gibbs Phase Rule. This is your degree of freedom. If you ask me, this is degrees of freedom. So already, I also mentioned this when I discuss the state of a system, state of an ideal gas, n moles of an ideal gas or of an ideal gas. Two ways: state of an ideal gas or state of n moles of an ideal gas. For example, so see here degrees of freedom. This is about phase rule, Gibbs phase rule. This is what the Gibbs phase rule is talking about. We are concerned. Gibbs gave very nice relationship. Quick, mathematically you can find out. And you will see practically this happens also. So what it is, for example, actually another thing is easier, even easier is y is function of x. Remember? Then what is this? The moment you say this is independent, right hand side is function of independent variable. Right hand side is independent variable. Left, if you say y is also variable, y is also a variable, but dependent variable. Dependent. Both are variable. Y versus x. Y is 4x square. Both are variable. X changes, y changes, x changes. But when we write this way, right hand side function of x means x can independently change, y will change following x dependently. Then when x is function of y, if you write x is function of y, then this is independent, this is dependent. This is independent, this is dependent. Changes. But anyway, we write, customarily we write y is function of x. So this is degree of freedom. For example, recall what you write, temperature, sir. Another thing I will add, mutually independent, unnecessary. It is understood. It should be independent or independent. Temperature, pressure, moles, ideal gas. As a system, the simplest system. Three degrees of freedom. 3 degrees of freedom. Three, three independent variables. 3 degrees of freedom. This is obtained from the phase rule. Ideal gas. Three is three. Count is three. We'll see also. We get three. F is we'll prove this. F is C minus P plus 2. This I told you. Ideal gas as system. Now what is state is given by how many? Why it is three? See, by the rule it is component gas. One say argon gas, say argon, say inert gas. One component gas, one gas, single phase. One minus two. Actually, this shows two, but I'll explain why it is three. This is actually if moles are acha, moles are okay. 2 hours over. 1 hour 59 minutes. So just stand by. Is over. So it is two. Actually, it looks two, but why it is three? When the this for giving acha acha acha. Wait a minute. Temperature is n. So n is okay 3. It is actually 2. It is 2 plus 1 when moles are unknown, number of moles, then it is 3. This 3. If moles, when is for 1 mole ideal gas, but for 1 mole, for example, Eg, for 1 mole ideal gas, or say 4 moles. All right. So 1 mole of ideal gas. What is the degree of freedom? This is right. If state is a function of what? Temperature of the ideal gas, pressure. Then what is it? What we achieve by fixing this independent variables, degree of freedom, phase rule? You can define the state of the system. To define the state of the system, 3 or 2. 2 actually by the phase rule it will be 2, but phase rule has certain restrictions that will explain actually. But it is for 1 mole or 2 mole for that matter. For 5 moles it is 2 only. So you know the moles. 2 moles say for example, 1 mole, since I have said 1 mole. 1 mole, you know the temperature. You fix the temperature independently. It's a 500 Kelvin. Pressure independently, 3 atmosphere. So 500 Kelvin, 3 atmosphere, 1 mole is the whole property. The state of the system is fully defined. Means all properties are known. What namely? Volume is known. PV is nRT. You know N is 1. P you know T V. R is the gas constant. And then once you know the temperature, you know the heat capacity. And you know the internal energy is a function of temperature, internal energy, enthalpy, etc. It is so all properties. So these are only these are variables or properties, but dependent. This is the case. This is the case. Okay. So I will actually this is actually the very uh, okay, introduction, also very simple introduction that I gave you. This what I connected with the beginning class, introductory classes, the Gibbs Phase Rule. But next day I will actually show you how to derive this. I will show that give you the derivation, okay, expensive derivation and applications of this. So thank you very much. So this is actually the today's okay. Okay, next day we'll pick up from this point. Okay, thank you very much. See you next class. Okay, thank you for your okay, cooperation and patience and your interest, devotion, etc. And okay, so call it a day. Next class. Okay.